Hi folks, Buckley here. Going to do some derivations of mechanical advantage for some simple machines. So if you're curious about where some of these equations came from for mechanical advantage, on your equation sheet that I provided to you for simple machines, we're going to go over that now. A lot of times these equations are just presented to you and you're told to use them, and I don't really think that's the greatest idea because you learn a lot by seeing where they come from, and they all come from the same basic principles. So we're using basically Newton's three laws, right? And the one that we use the most is the action-reaction with simple machines, right? And we're also using conservation of energy, COE. So that's one that we've been pulling out a lot. Okay, so let's start with the first one, which is the lever. And I did a derivation of the lever in class. I'm just going to do it again because I want to make sure everybody understands it. And we're going to apply this conservation of energy principle. So let's say for the lever, we have ourselves, let's make a little lever here that we're going to use to lift a heavy object. So here's like a big rock, right? We got this big rock and it's got a weight to it, right? Its weight is I don't know, 1,000 pounds, right? So this weight, using our nomenclature, this would be the F out, right? That we're trying to lift. And the lever, we're going to make sure that whatever we're using to lift it has a mechanical advantage. We don't want to put 1,000 pounds in. So I'm going to make my fulcrum for the lever closer to the rock than where I'm going to apply the load. So here's me, okay, and I'm going to step on this or push on it really hard with some input force, F in, to lift this heavy object. Okay, and I'm just going to deal in F out and F in. And then the important information that I need, geometrically speaking, right, is I'm going to call this R in, and this guy R out. Now you can call them D in and D out, that's fine too, but I'll just stick with R in and R out. Okay, so using conservation of energy, I need to get some information about the distances that these forces would travel, right? So if I can imagine that, because basically I have work equals force times distance, and I know from conservation of energy, or conservation of work here, right, conservation of energy, conservation of work, I'm using them together, work in is going to be equal to work out, right? So on the input side, I'd have F in times some distance traveled in, which I'm going to leave as a question mark right now, is equal to F out times some distance traveled out. And the question is, what are these distances? Okay, so if I am to apply, let's say I want to lift this rock a little bit, right? What's going to happen is it's going to kind of travel in an arc, right? So it's going to sort of arc up. Okay, and it's and this plank on this side is going to arc down, and the angle of that arc is going to be the same, right? So I can express the distance traveled along this path as some fraction of a full circle, right? So here would be a full circle, and it's going to travel some percentage of that full circle. Okay, so I'm just going to make up a percentage. I'm going to say it's 1/100th of a circle in just lifting this rock up the ground, off the ground, right? And on this side, I'm traveling 1/100th of a circle as well, but the radius of that circle is going to be bigger. So I'm traveling 1/100th of a circle defined by the distance between the radius, right? The distance between the fulcrum and the line of action of my force, right? So this guy is going to travel a rather small circle, right? And this guy out here is going to travel a rather big circle, a fraction of a rather big circle, okay? All right, so this distance, I could say, is 1/100th of one full circumference of a circle defined by the radius R in, right? So 2 pi R in is the total circumference of the circle, right? So, and then over here, conversely, I would be traveling 1/100th of 2 pi R out. Okay, so putting these together, I get F in times 1/100th 2 pi r in. And again, the 100th is arbitrary, right? I could make that another variable, you know, alpha or something. And you'll see they're going to cancel out. 2 pi r out. Okay, and these guys are equal, so these terms here, that's just all going to drop out. So I get F in R in. Oh goodness, I'm running out of room. F in R in is equal to F out R out. Okay. And I define mechanical advantage is equal to F out divided by F in, right? And if I rearrange these terms, I'm going to move F in over here, right? And R out is going to come over here. I wind up getting F out over F in is equal to R in over R out. Right? And this is where I get, on your equation sheet, I just list this, right? Because typically you don't have sensors to measure the forces. What you've got is a ruler, right? So this is the equation that you've got on your equation sheet for the lever. All right, so that's the lever. Let's move on. Let's move on, and actually let's do a pulley system. We'll do the pulleys, okay? So pulley. Let's start with a really simple pulley. So pulleys on your equation sheet, I've shown 3 common pulleys and given their mechanical advantages, but I'd like you to be able to kind of derive them for any type of pulley. So let's say you've got a pulley, and this is your weight, or as we now call it, F out, right? You're trying to lift some object. You're running it around this pulley. I'm showing it not contacting the pulley, but this is basically, right, this is a pulley. Okay, and you are over here, and you are pulling, right? You're pulling that up. So you're pulling this rope towards you. So you're applying an F in. Okay, so the mechanical advantage is equal to F out divided by F in, right? And the same principle applies that work in is equal to work out, right? Conservation of energy applies in this situation. So we've got F in times some distance traveled in is equal to F out times some distance traveled out. And the distance traveled, you got to think about how much rope you're pulling, okay? So if I am to pull this weight up this distance, D out, I need, with this pulley arrangement, this one pulley, I need to pull this exact same amount of rope on the other side, right? So D in this situation, if this is pulled up this way, I have pulled this length of rope towards me, right? So D in this situation is equal to D out for pulley as shown, right? This type of pulley. No matter if I'm pulling down, if I'm pulling to the side, doesn't matter, I'm still pulling D out, right? So if D in is equal to D out, plugging that in up here, then F in must equal F out, and my mechanical advantage must equal 1, right? So this pulley here, this arrangement, I've got MA equals 1, right? Which is what you get on your equation sheet. Okay. Now, let's look at a different pulley. Let's take same one pulley, right? But it's connected directly to the weight, right? So the pulley is sitting, maybe we got like a rigid bar or a small length of rope or something, right? The pulley itself is connected to the weight. And the rope runs up and around, okay? And it's fixed, it's pinned down right here. And I am standing here pulling up, right? So this is my F in. This is my F in. And this weight, again, is my F out. Okay. So, when I pull up, so if this weight were to travel from here to here, right? Here to here, I would need to pull twice the length of rope. And remember, I've got a whole bunch of rope sitting over here, right? So I got plenty of rope. To move this pulley, or to move this weight, this distance, I would need to pull twice as much rope out on this side. So I get D in is equal to 2D out. F in D in is equal to F out D out. That's my same conservation of energy expression, but just by the geometry here, my D in is going to be twice. I need to pull twice the length of rope up to move this same distance, right? So plugging this guy in down here, right, I get F in times 2D out is equal to F out times D out. 2F in, so my D outs are going to cancel. 2F in is equal to F out. Then dividing by F in, right, so I get F out divided by F in is equal to 2. F out divided by F in is nothing but the mechanical advantage. So the mechanical advantage of this system is equal to 2. All right. I want to solve this problem a slightly different way as well, okay, because that's going to help us out when we get to our other pulley problems. So I just reasoned this out using conservation of energy, right, pulling a weight over a distance. I'm now going to use statics. So statics is based on Newton's second law. Sum of the forces is equal to ma, but I set a equal to 0, right? Things stand still. So I'm going to use sum of the forces is equal to 0 because this is basically static, right? Basically static. Even though I'm moving the weight, it's really, really slow. There's no real acceleration to the system. So I'm going to use this arrangement here. Sum of the forces is equal to 0 to also derive ma equals 2 in this example, okay? So I'm going to do it a slightly different way because that's going to make it easier for our other expressions. It's really hard to reason out how much rope you're pulling relative to how far the weight's moving as you get more complicated with your pulley systems. All right? Okay. So let's look at this pulley system again. So I've got a pulley attached to a weight. Just going to label it F out. I've got a string, a rope that's coming around, and I'm pulling on the rope. And this guy's fixed here, right? It's locked down. Okay. One thing to know about rope, guys, is that the tension in a rope is always the same, right? So tension or force, it's a pulling force, ropes can only be loaded in tension, is always the same. Unless, I'll put a little asterisk, unless friction. All right, but we're assuming frictionless, okay? So unless friction, tension in the rope is all the same. And we're assuming this is a frictionless pulley, okay? So anywhere I cut this rope, I'm going to have the same tension. Tension is going to be the same here, here, all around the pulley, and then there. Right? And I know that my tension is always equal to what I'm applying, right? So in a rope, if I'm pulling, I'm the only thing that's exerting a force on that rope, right? So if I were to cut the rope here, what I'd be left with is the pulley with the force out coming down, me pulling on the rope on this side, and then because I've cut that rope, me pulling on this side as well. This is what we call a free body diagram. You'll get more into this in statics, okay? And statics is a common course for civil engineers, mechanical engineers. We wind up getting some chemical engineers even who take it. It's kind of fun, okay? So looking at this, if I look at the sum of the forces in the x and the y direction, this is a planar problem. In x direction, there's nothing going on, so I'm just not even going to worry about that. So sum of the forces in the y equal to 0 gives me a positive 2Fn, Fn plus Fn, minus F out, right? So I get 2Fn is equal to F out divided by Fn is equal to 2. F out divided by Fn is my mechanical advantage. So that's another way to derive it. Okay. And this way to derive systems is also to derive the mechanical advantage of pulley systems is more flexible. I can use it for however complex the pulley system is. As proof, let's skip on to one of the other examples that was provided on your equation sheet, okay, which is a complicated pulley system that looks like this. Okay, you've got a weight, which again we're going to call F out, and it's connected actually to two pulleys. So there's a little pulley and then a bigger pulley, right? And these pulleys are linked together. And on the top, right, you've got kind of the same thing. So up in the ceiling, you've got a big pulley and a little pulley, again, both linked together. And then you got to run the rope around all this stuff. So what we do is we start with the little pulleys, and we run a loop-de-loop around the little pulleys, and then we run a loop-de-loop around the big pulleys, and then we come out. This is called a block and tackle. Now you're going to see this like at construction sites. You see it a lot, like maybe some flagpoles, ships. If you sail, okay, a lot of your sails have this type of system to them. Okay, so this is your input force. That's the force that you're pulling. You can get a lot bigger mechanical advantage in this scenario. All right, so this is one continuous string, right? One continuous rope. So I know that anywhere here, the tension in that rope is always Fn, what I'm applying with my hands. So I'm going to use that same principle, the same four-body principle, and I'm going to cut my ropes virtually in my mind and isolate this system. Okay, so when I do that, I've got F out, and then I have 1, 2, 3, 4, 1, 2, 3, 4 pulleys coming up from it. This guy, this guy, this guy, this guy. 4 strands of that same rope coming up, right? This strand doesn't count. It's not connected to this system. It's very important. I could pull this way and it would be the same. Okay, this guy don't matter. 1, 2, 3, 4. Okay, and obviously F out is coming down this way. And each of these are Fn. Fn, 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 Fn. So what I get when I do sum of forces in y is equal to 0 here, I get 4Fn minus F out is equal to 0. You can see that's going to get me F out is equal to 4Fn. F out divided by Fn is equal to 4, and that's my mechanical advantage, right? So I get Ma is equal to 4 for this type of system. All right, I couldn't, maybe you guys can do it, but I can't in my head reason that it's going to be 4 times, I got to pull 4 times this distance to close the gap, right? I can't see it. I need to do it this way. All right, so that's derivation for ropes. Now, let's finish out with gears, okay? Because gears are interesting. Gears are very interesting. The other one that I could, so the wedge is pretty much the same proof as the inclined plane, which I went over in class. And the wheel and axle is pretty much the same proof as the lever. Okay, so there's not much interesting happening between those guys. But the only one interesting left is really to talk about gears. So let's move on to gears. All right. So I want to show you where the relationship for mechanical advantage of gears comes from. Right, so with gears, and I'm going to do this, I'm actually not going to do it with a conservation of energy, okay, because that's a little beyond the scope of this course. I'm going to derive those same equations using a couple other principles, okay, a couple other principles. So we know that if you're to look at your equation sheet, you get the mechanical advantage of a gear set. So let's start with a gear set that looks like this. So this is our input gear. It's got a known angular velocity and a known input torque, right? We'll also say it's got a known diameter, right? A known, this being the diameter of it. Or I'm going to put in parentheses here or beneath it, or a known number of teeth, right? Because the teeth on gears need to be the same size in a gear set. They need to match, right? So, another equivalent to diameter would just be number of teeth. Okay, on this side, we've got this is our input, and this is our output gear. We've got omega out, we've got torque out, we've got D out, or number of teeth out, okay? And our handy-dandy equation sheet tells us that the mechanical advantage is equal to the torque out divided by the torque in, which is equal to the angular velocity in divided by the angular velocity out, which is equal to the diameter out divided by the diameter in, and then not a big jump, the number of teeth out divided by the number of teeth in. So we're going to talk about where does this all come from, right? Where does all this stuff come from? Okay. So with gears, one thing that's happening that's very important. So the first thing about this expression is mechanical advantage ma equals torque out divided by torque in. This is by definition. Just like we defined ma for a linear system is equal to force out divided by force in. We've defined that, okay? So this is by definition. So this is a given, right? And it's really a matter of why these guys, why does it also equal the ratio of the angular velocities or the ratio of the number of teeth, right? Okay, so let's see if we can't derive relationships between torque and these other parameters. So I want to zoom in on what's happening here when teeth contact in a gear. So when teeth contact in a gear, so here's my one gear and here's my other gear, and there's teeth here, right? And these teeth are they're mating with each other. They're mating with each other. And let's say this guy is spinning this way, and this guy then would be spinning this way, right? That means that this tooth is pushing, it's pushing down on this tooth, and this tooth, action-reaction, is pushing back up. And with gears, these expressions that we just derived are related to, or they apply when the gears are not accelerating. They're moving at a steady state, right? So this means that when there's no acceleration here, we have an action-reaction pair. So we're using Newton's third law, and actually the same thing would apply even if they are accelerating, but Newton's third law. F on this side is equal to F on this side, right? Action-reaction pair. Now, let's see if we can't relate these forces that are happening at the teeth, right where they're connecting, right, to some other parameters. So this force that's happening here is related to the torque. So the force on this tooth here, if I've got a force, right, that force times this distance, which is d in divided by 2, right? F times d in divided by 2 is equal to the input torque, right? That's the torque. Or equivalently, the torque, Tn, is causing that force, right? And you can see where I'm going with this. So on the output side, you've got the same phenomenon, right? So for my bigger output gear, I've got a force acting at a distance d out divided by 2, and that's going to be equal to the output torque, because that's what's driving it, right? So I get F times d out over 2 is equal to torque out. All right, these F's are equal, right? So let me solve this expression for F. So I get F is equal to torque in, 2 times torque in divided by dn. And over here, I get F is equal to 2 times torque out divided by d out. Setting the F's equal, I get 2 times torque in divided by d in is equal to 2 times torque out divided by d out. The 2's cancel, and I can rearrange this, right, so that I can get my expression, my defined expression for mechanical advantage. So if I rearrange it, I'm going to divide by T in and multiply by T out, right? So I get T out divided by torque out divided by torque in, which is my mechanical advantage, is equal to d out divided by d in. All right, and again, because the tooth size, because the tooth size on each of these gears must be the same in order for them to mate, d out is proportional to n out, right? And d in to n in. So I can replace these with n's, the number of teeth. So I've just proven this part, right? That you can calculate a gear ratio or mechanical advantage just by looking at the number of teeth or the diameter, number of teeth or diameter of a gear. And I've used what's happening at the tooth, the interaction at the tooth, to prove that. Okay. One more little thing with gears, right? We still haven't figured out how these two are related, right? Okay, so I've got these gears. This is in, out. I'm just redrawing because I've got a new fresh piece of paper. Omega in, torque in, omega out, torque out, diameter in, number of teeth in, diameter out, number of teeth out. Okay. The other thing that's interesting about gears is that the speed, what's happening at this point on both gears, is that the teeth are physically moving at the same speed. Okay, so linear velocity at contact point, at contact between gears, is equal, right? It's equal between these two, meaning that the speed that one gear is going past each other is equal to the speed that the other gear is going, right? Just opposite directions. If the speeds aren't equal, the gears slip past each other. So speed is equal to distance traveled divided by time, right? So the distance traveled is pi, it's one circumference, right? And to change it to a velocity, right, would be, you'd also multiply by the revolutions per second, right? So what you wind up getting here is that the velocity at any given point, the speed on the surface of this, is pi d, we'll say we're on the input here, pi d in omega in is equal to pi d out omega out. Knock these out, right? This tells us that omega in divided by omega out is equal to d out divided by d in. And we already know d out divided by d in is the mechanical advantage, right? So that means mechanical advantage is also equal to omega in divided by omega out, just by matching up the speeds. All right, so that's another way to derive mechanical advantage. Okay, so that's what I have to say about gears. I do want to show you one thing. I promised you a derivation of what's going on with compound gear trains. Compound gear trains. So compound gears you've got gears that share an axle. So here's one gear set. We'll call this A and B to be consistent with your equation sheet. We've got C, so these guys, B and C share an axle, and then D just meshes with C. So A and B mesh with each other, and C and D mesh with each other. And we've talked about gear trains, and that gear trains are compound machines, right? So it's just sets of these two gears that are linked together, right? So their overall MA is multiplied. MA1 of gear train 1, MA of gear train 2, MA of gear train 3, right? So let's look at first the MA of this gear train. And let's assume that we know the tooth count on all of these. So MA of this, and I'll call this MA of BA, is equal to N of B divided by N of A. Output, number of teeth on the output divided by number of teeth on the input. All right, the next gear train is actually this guy here, right? And this guy here is interesting because we can't use it's basically not a gear set. It's just one machine that looks like this, right? You got two gears sharing a common axle. So two gears sharing a common axle share the same speed, right? And remember, our expression for mechanical advantage is equal to torque in or torque out divided by torque in is equal to omega in divided by omega out. So if we're looking at C and B here, and we know because they're on the same axle, every time it revolves, B and C are going together, right? Their speed is the same. And we're considering C to be the output and B to be the input. This means that omega C is equal to omega B, omega in is equal to omega out, and mechanical advantage here is equal to 1 then, right? This is equal to 1. Also note that the torques are going to wind up being the same, just by that definition. Just by the fact they share an axle and they're always going at the same speed, the mechanical advantage is going to be 1, right? So MA of this set here, MA of CB is equal to 1, because their speeds are equal because they share this. And then we've got our last set here, MA of DC is equal to ND divided by NC. And the compound mechanical advantage is equal to MABA times MACB times MADC. And MACB is just equal to 1. This guy is equal to NB over NA, and this guy is equal to ND over NC. So you get the mechanical advantage of this complete gear set is NB over NA times ND over NC. Okay? That's a compound gear. All right, that's all I got for you. Thanks for watching, and good luck with using those expressions. Now you know a little bit more about them. Thanks.